Lammer precision, behavior of an electron in an external magnetic field. So in an atom, the electron is moving around the nucleus in a circular orbit, and this electron is a charged particle, and the motion of this charged particle will produce a current, and hence the electron moving in a circular orbit is equivalent to a current carrying loop, or the orbit can be considered as a magnetic dipole. And when this orbit is placed in an external magnetic field, then the orbit precesses about the direction of the field, and this is known as Larmour precision, and the frequency with which the orbit precesses about the direction of the magnetic field is called the Lammer frequency. So here we can consider the case of an electron. So this is the nucleus, and here we are considering an electron which is moving around the nucleus in a circular path. This is the center point, and assume that the electron is moving with a velocity v, and this electron is moving with a velocity v, and electron has some mass m, and hence it has an angular momentum, and that angular momentum can be represented as perpendicular to the plane in which the electron is moving. Here the plane is, this is the plane in which the electron is moving, and hence we can consider this angular momentum as this, where L is the angular momentum. And we know that in the case of an electron moving around the nucleus, it is equivalent to a current loop, and the orbit can be considered as a magnetic dipole. Hence a magnetic dipole moment will be induced in it, and this magnetic dipole moment will be along the same axis but opposite to the direction of the angular momentum, and this can be represented as, this is the magnetic dipole direction of the magnetic dipole moment. Here the magnetic dipole moment can be represented as mu L. This mu L and L can be related by a relation, that is mu L is equal to E by 2m into this L. That is, the magnetic dipole moment and angular momentum can be related by this relation. And when this dipole, this magnetic dipole, it is placed in an external magnetic field. So this is an external magnetic field. External magnetic field, it can be named as B. This is the external magnetic field. When this magnetic dipole is placed in an external magnetic field, then this dipole experiences a torque, and this torque can be represented as tau is equal to this mu L cross B. This tau will be perpendicular to both mu L and B. That is, tau will be perpendicular to mu L and B. And tau will be perpendicular to mu L means tau will be perpendicular to L also. That is, tau will be perpendicular to mu L, B and L. Then we know that the torque can be represented as, the rate of change of angular momentum, where dl is the change in angular momentum in a time dt. That is, according to this equation, the torque tau will be in the same direction as of dl. So here this is B and this is L or mu L, then torque will be perpendicular to both this direction. This is torque acting in this direction. So both are perpendicular. Here we can represent the dl as in the same direction as a tau. So we can say this is L, and then we can represent this dl as, this is the dl. dl is this one. So this is the dl. So according to this equation, that is, torque will be in the same direction as the dl. So dl can be represented as this direction. But we can calculate the Lammer frequency. For that, we are assuming that here the magnitude of L remains constant. Magnitude of L remains constant, and also the theta between the B and L is constant. Then we can represent this as this is the magnetic field and this is the angular momentum component. This is magnetic field and this is the angular momentum component L. And dl means this is the dl because the torque is acting perpendicular to this L. So as a result of this torque, it can either move this or this direction. But if it move in this direction, then the theta will vary. The L and the theta will remains constant. So it cannot move like this. Then this torque can only change, this angular momentum can only change its direction, not its magnitude. Its magnitude L is constant and this theta is constant. Then it can change like this. That is, it changes its direction from this position to this one and this one. That is, it just precise about this field direction. And it is called Lammer precision. Lammer, the frequency is called Lammer frequency. So here we can represent the variation as, that is, it can change either this direction or around this field. So we can here consider a circular cone like this. Consider a circular cone. If the center of the cone is this one, then we can consider this radius as this one. This is the change dl. And we know that the angular velocity omega is equal to d phi by dt, where phi is, this is the angle. So here the d phi can be represented as omega into dt. Hence this angle will be omega into dt. That is change from this position to this position. The change dl from this position to this position. That is, this dl and this angle is omega into dt. And if we consider this as the radius of this circle, so this radius with respect to this theta we can represent, because this is L and this will be opposite side, that is L sin theta. This will be L sin theta. So we can consider the equation arc by radius equal to angle. Arc by radius is equal to angle, that is arc is dl. Radius is L sin theta. Angle is this omega into dt. So this is the arc by radius equal to angle. We can modify this equation, that is omega is dl by dt into 1 by L sin theta. dl by dt into 1 by L sin theta. But dl by dt is the change in angular momentum, rate of change of angular momentum. This can be represented as tau. That is, it can be represented as tau into 1 by L sin theta. But tau is equal to, this is tau, mu cross B or mu B sin theta. Then we can represent it as mu L B sin theta divided by L sin theta. So it will give mu L B by L. But this mu L and L are related using this equation. Mu L is equal to E by 2m into L. So we can write it as, that is, the omega is equal to mu L is E by 2m into L divided by L into B. That is, omega can be represented as omega is equal to E by 2m into B. But we know that the period t is equal to 2 pi by omega. Or the frequency, omega can be represented in terms of frequency. Omega is equal to 2 pi by t or 2 pi f. Omega is equal to 2 pi f is equal to E by 2m into B. Therefore, the frequency f, the Lammer precision frequency f can be written as E by 4 pi m into B. This is the expression for the Lammer precision frequency. That is, the frequency f is equal to E, where E is the charge of the electron and m is the mass of the electron and B is the applied magnetic field. So here we can consider a cone around this magnetic field. Similarly, if this is L, here the change in L is represented as this conical structure. Then similarly, if L is changing, then the change in mu L is also like that. The mu L can also possess a conical structure here. So here the L just precess about this magnetic field. Means L means it is the angular momentum. So the angular momentum is because of this orbital motion of this electron. So we can say this orbit, it just precess about the field direction.